Welcome back, my dear subscribers. I'm going to discuss today about shear and bending and beams using BS5950. Okay, so let's start. Uh, Let me just acknowledge my author reference of the book that I'm using for this discussion. This is from the Design of Structural Elements by Chanakya Arya. Okay, so yeah, let's start. So just some sort of brief review about flexural stress. So here we have the general formula, MC over I, and then the relationship between C, if you have this beam, you have the neutral axis. This is the C that we are taking into consideration. If this is for rectangular section. And then you can have this, these values, 6 MPD squared for rectangular section. And then for our discussion, especially we are discussing about the structural steel. This relationship is very important, is I over C, and then you have for rectangular section this one. But for structural steel, we are much very specific on this formula. Yeah, for we usually get the moment, and then we just get the required section modulus that we can get from the table, which I'm going to present to you later. And then we have here some just to show some behavior of the material when it's subjected to flexion. You have here the moment, you have your tension, and then here's the compression. And then some we have here example of the shear and the moment diagram by which we are really we need this value of moment for us to get what would be the required section modulus that we can get from the table. Okay, so we have here also some values that we could use for different types of loading on our structure, if it's concentrated at the midspan and so on. And these values with the corresponding shear force, maximum shear force, maximum bending moment, then you have the deflection. Now, for initial section, it is important for us to know that the applied moment should be less than the capacity, of course. The capacity should be bigger to that of the applied moment. For example, if you have here this structure, and then you have here the load, then this will create a moment. Obviously here, this moment should be greater than the capacity, so that it would be safe. And from our relationship earlier, that we can have, okay, here, Py over S, we can compute for the required S out of this actual moment that we had. Then we can get the section modulus, and then what would be the size of your, let's say, structural steel that we can get from the table, which I'm going to show to you later. And then some condition that we have to check first to identify what class of section are we going to analyze, right? Because there are some limiting width to thickness ratio that we are going to check based on the table 11 of BS5950. So if it is outstanding element of compression flange, FB over T, which this one could be taken from the table, is less than with this value. Take note that this is equal to say E 275 over PY or rho Y, by which if we have this 275, then we can have this value equal to 1. But if it's less than, then there could be a different value that we have to check from there. Okay, if it satisfies this condition, then we can say that this one's plastic, otherwise it's compact or semi-compact. The thing here is we have to check with this one necessary for our calculation. Okay. And then you have here, of course, once we get the initial section, then we check the shear values. Okay. The shear force or the FB should not exceed the shear capacity. Of course, the capacity should always be bigger than the actual or the applied shear or the shear force for us to be safe. Where PV is equal to 0.6 PY AV. F is the area, the shear area. TD, considering you are just in an H and channel section, you have the T is for the thickness, and then the depth we're considering for the web. Okay, you get here the D and you have here the T, which is given also in the table. Also states that when the buckling ratio D over T of the web exceeds, okay, then the web should be additionally checked for shear buckling if it exceeds, all right, this value. To check it. Then of course, our we have to check also if it's low shear and moment capacity. If it's low shear, and then check also the moment capacity. According to the clause in BS5950, 4.2.1.1 at critical points of combination, maximum moment and existent shear, and then maximum shear and coexistent moment should be checked. So how do we check this? If the coexistent shear FV is less than 0.6 PV, then this is low shear load. Take note of this one. Otherwise, if it's greater than 0.6 PV, what is PV here? Okay. This is PV. If it's greater than 0.6 or 60% of the PV, but less than PV, then it is high shear load. When the shear load is low, the moment capacity of the section is calculated according to the clause 4252 of BS5950, which is being now shown in this formula 4.7. Okay, so for class 1 plastic or class 2 compact section, we can use this one. Moment capacity is equal to this design strength of the steel and then the section modulus, plastic section modulus. But take note, you should also check it, and it should be less than 1.2 of the design strength of steel and then this elastic section modulus. So these are the conditions that you have to check when you are having a class 1 plastic or class 2 compact section. The additional check, you have this one, MC, should be less than, yes, it is to guard against plastic deformations under serviceability loads, and if applicable only, and is applicable only to simply supported and cantilever beam. For other beam types, this limit should be, okay, this one. If it is simply supported, we use 1.2. Other types of beam, we use 1.5. Okay, so for class 3, we are going to use this one. Okay, take note, this one is class 1 and class 2 that we have from this. Remember, from this we have here class 1, class 2, class 3. Okay, for class 3, you have here MC is equal to PYZ. You consider this, what is Z? Elastic modulus. And then, or alternatively, you can use PYSF, but should be less than 1.2 PYZ, similar to this one. This is more about elastic modulus. SF is the effective plastic modulus clause of 356 of BS5950. And other symbols are noted in the equation 4.7. This one. So for class 4 cylinder section, which are not here, okay, then you can have this also. Okay. Anyway, I'm going to be focusing more here about low shear load. Okay. But it is important for us to take note what are those satisfying conditions that you have to achieve. That's for plastic class 1, class 2, class 3, or class 4. So for example, we have here, okay, this is our floor plan part, extract of the floor plan. Of course, we, as part of our analysis, if there is a combination of structural steel and then slab is concrete, then of course we have to take consideration of, let's say for a conservative analysis, we can just consider this area to be carried by this cantilever beam. Let's say this one is cantilever beam, and then some load given, example here with the concrete is this one. Okay, but for some consideration, you can have this 45 degrees. Okay, so just say we consider just this one. Okay, so if you have here, of course, moment here is coming. Okay, you have here the moment, and then you have your shear. Of course, your moment is just equal to the resultant load here, which is 18.08 times 3, and then the moment arm, which is equal to 1.5. In other words, you have 18.08 times 3. This becomes kilonewton already. Multiply by 1.5 meter. Then you got 81.36. This will be your moment. And this will be the the applied moment that you are going to use in determining the section modulus. And then of course you have also shear here, which is just equal to the load, equivalent to 54.24 kilonewton or 18.08 kilonewton meter times 3 meter. You got 54.24 kilonewtons. As just a simple calculation, we are going to calculate moment and shear, because this one we are going to use. Okay, so as we calculated earlier, the ultimate moment capacity, or the moment or M, is this one at 1.36. And let's say we have the design strength of steel is 275 megapascal. As we say, the is X, or the required S, okay, we can say like this, is just equal to this moment divided by the given, or the designed strength of steel, with the conversion for us to get centimeter to the power of 3 as given in the table. And we have to get at least 295 or more to make it safe. So the requirement is 295.85. So we will look for a bigger value of this one. From the table, this could be the option 254 by 102 by 25. This has a value of section modulus of 306. S, take note, this is plastic. And then the other one, is 313. But considering these two, it would be better to use this one. This is lighter weight, 25 kilograms per meter. Of course, when you have lighter weight, that would be economical, better to use. So as you can see here, you have here the section modulus, or plastic section modulus, which plastic section modulus is 306. Okay, and you have this one, 25. Okay, 254 by 102 by 25. You have here also 313, 30. Better to use this one. Okay, as I said earlier. Okay, so once you have that one, then we can check the section classification. Class A or class 1, class 2, as you remember this one. So we compute B over T, which is B over T. This one is B over T. Okay, so from here, B over T is 6.07. How about D over T, which is about web? Okay, D over T. Effective depth, okay, this one. Where's effective depth? This one. Depth between fillets. Okay, we have 36.9. So we have here B over T 6.07, 36.9. Take note that we have this value equivalent to 1, because this is just the same as 275, so we can get here 1. So this is less than 9, this is less than 80, and it satisfies plus 1 plastic. See, this is plus 1 plastic. Okay. Now, so this is a low shear. Okay, low shear. Show low shear load. Okay, this is a low shear load actually, which I'm here is a low shear load. How are you going to achieve low shear load? This one should satisfy less than 0.6 PV. Okay, but this one first, we were able to determine that this is a class 1 plastic, class 1. Now, we have this checking also for shear strength. When D over T is less than 7 over E, the shear buckling need not to be considered. When D over T is less than 7 over E. Okay, this is coming from here. Okay. Okay, this one. When it exceeds, then we have to check the buckling. Okay, how do we satisfy if it is a low shear load? It should be less than 0.6 PV. PV is your 0.6, PY is 275, T is given from the table, which is 6.1, and then you have effective depth, it's also 257, which are you going to get it from here? D here, T here, small t here, 6.1. Okay, so we have this one, okay, 6.1. So all from the table, these values are taken from the table, as I have shown to you. Then we have this PV, okay, 0.6 of that, 0.6 of 258.67 is 155.2. And then our FV or VC or the shear, which we calculated earlier to be this one, 54.24, is still less than that 0.6 of PV. Okay, this is PV. This is PV. 0.6 of that or 60% is 155.2. Still, our FV or VC is less than the 155.2. So this is a low shear load. Otherwise, if it's greater than 0.6 PV, we have to check also with the PV if it is within the range. Okay, so this one is low shear load. If it's within the range, we can say that it's highest shear load. We have to look for another condition or equation that is applicable for high shear load. This one is for low shear load. Bending moment capacity. So our bending moment capacity, you have Py times S, which we get from our initial selection of our structural steel, which we used for identify from the table, and we can get this one. Now we have to check if it is less than this one. 1.2 PYZ, 1.2, you have PY from the table, Z also from the table, 265. Section modulus, which is elastic. We can have this one. So see, this one is less than 87.45. So the moment capacity, okay, this is from this condition, okay? For a class 1 plastic, also applicable for class 2, that MZ should be equal to PYS, but has to be less than 1.2 PYZ. Otherwise, if it exceeds, this one should be the limit. Okay, this value should not exceed 1.2 PYZ. If it exceeds, then we use the limiting value. Now let us consider. Let us compute what will be the actual moment. Self weight. You have our selection structural steel. Let's say you get some 40% that you want to add. As an example, and then convert it into Newton meter or Newton meter. We have this one, which is multiplied by 9.81. So the moment of self weight, you have this 1.34 multiplied by this span 3 and then the lever arm, then you get 1.53 kilonewton meter. Add it, okay, with this applied moment from the load coming from the slab, add with the self weight, and we have this one. So MT is 82.89. The total applied moment, but our capacity is 84, meaning it's safe. Okay, this one is still less than our MC. Okay, our capacity is 84, something like that, and applied moment is only 82. In other words, this one is safe. Our selection is suitable. Okay, so that's all for this discussion, for this tutorial, and just keep updated with my new video that I'm going to discuss more in the coming days. Thank you.